Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. I'm really excited about today's topic. We're diving deep into the current state of AI and what's needed to really achieve, true artificial general intelligence, or AGI.
Yeah, absolutely. It's a massive question, isn't it? AGI. Feels like we're simultaneously incredibly close and also miles away. Like, we have these amazing AI models doing incredible things, and yet,
And yet, yeah, I completely agree. I think we're maybe being a bit too optimistic about the current trajectory. Like, are we actually on the right path, or are we just, getting very good at pattern matching? There's a difference between that and actual intelligence.
Right. I think so too. And that's kind of what I always come back to, the understanding of the underlying principles of what intelligence truly is. I mean, we see impressive results with deep learning, sure, but I often feel like it's a very brute force approach, lacking that flexibility and true understanding we see in biological systems.
I hear you. I mean, it's easy to get swept up in the hype, with the latest large language models generating human quality text or image recognition algorithms that are better than any of us. But to me, it all points to the need to ground these AIs more firmly in actual neuroscience. We need to be looking at how actual intelligence, biological intelligence works. We need to understand the brain's architecture better and try and replicate some of those processes in our AIs.
yes, and that's where deep learning excels. I mean, look, yes, we may not have exactly replicated the brain, but we have made systems inspired by the brain's neural networks. And these are the same systems that are currently achieving state-of-the-art results. These systems are able to learn from data in a way that mimics some of the fundamental processes we see in neuroscience, such as hierarchical feature extraction and nonlinear transformations. For example, the convolutional layers in a CNN. That mimics the way visual processing happens in the brain. It's a process that starts at edges and basic shapes and progressively builds to more and more complex representations of an image. And it's the same with language and audio. We're extracting features using models inspired by neuroscience, and it's working.
But I think the inspiration bit is key there, right? I mean, yes, we use the term neural networks, but are they really doing what a real neural network in the brain is doing? It's like using the same basic building blocks and saying you've built a cathedral when all you've got is a block of Lego. The brain is so much more complex. We're glossing over how different brain regions communicate, the different types of neurons and their precise functions, the importance of temporal dynamics and feedback loops, the whole symbolic processing, deep learning. As powerful as it is, it's kind of like a really fancy curve-fitting tool. It doesn't really understand the world.
Yeah, I agree. And I feel like that lack of understanding comes from the fact we're missing some core fundamental algorithm or representation framework. The current approach in deep learning seems very much data-driven, a brute force approach with tons of data, which, works reasonably well, but it's not very generalizable. I mean, think about how humans learn. We can see a single object, understand that it's a cube, for example, and be able to identify other cubes of different sizes, textures, orientations in different environments almost instantly. Whereas, current AIs often require massive amounts of training data for each scenario. For me, that points to the fact that it's not capturing the underlying invariant relationships that are crucial to intelligence. We need to be able to move beyond just raw sensory data. There needs to be a level of abstraction that can generalize.
Exactly. So, we could be looking at more biologically plausible models. Models that actually try to replicate the way the brain processes information. For example, the concept of a cortical column, a functional unit in the brain, which does seem to perform specific computations, or looking at the actual spike trains in the brain, how the neurons communicate, rather than, a floating point number activation. Maybe we're trying to use the wrong underlying mathematics. I mean, there is a new focus on more neuromorphic hardware, which could offer better computational efficiency when running this type of model. And I think that's a really promising direction.
But I think you're underestimating how much deep learning has already achieved. For example, success of transformer networks and large language models shows the power of learning complex relationships from vast datasets, and these models are very generalizable. I mean, sure, a deep learning model doesn't understand a concept in the same way a human does, but it's capturing the underlying statistical regularities in the data. And the more data we throw at it, the better it gets. We are literally seeing emergent behavior in these models. They weren't explicitly trained to do what they're doing. They learned it themselves. So I think if we just continue with the scaling trend with bigger models and more data, we will eventually get to AGI. There are papers literally showing how scaling deep learning has resulted in the emergence of novel abilities in language models, and it's literally mind-blowing what is possible. And also, we are constantly making advancements to the models. There are research papers every day on making the current models better.
Emergent behavior or clever pattern matching. I'm still not convinced that throwing more data at these models is the key. These language models might be fantastic at mimicking human language. They can generate poems or write code, but do they understand what they are writing? It's like the Chinese room argument. They are manipulating symbols, but without understanding their meaning. I think we need to focus more on systems that combine the power of neural networks with symbolic reasoning, neuro-symbolic approaches. We need models that can represent knowledge in a structured way, that can do logical inference, not just like associative memory. Models that can operate with abstract concepts and perform reasoning about the world.
Yes, and I would argue that symbolic reasoning alone is not enough either, although it's necessary. I think it also needs to be grounded in a spatiotemporal understanding of the world. When we're thinking, we're not just manipulating symbols, we're imagining a space, we're picturing things moving, we're thinking in 3D and through time. Like, our intelligence is deeply rooted in our perception of the physical world. Deep learning, as good as it is, doesn't seem to have a good grasp of space and time. And I think we need an algorithm that can handle that sort of reasoning. Like, think about how you can watch a basketball game and follow a complex series of moves, understand each player's role, anticipate future events. To me, it seems that a lot of that comes down to some deep level of spatiotemporal transformation, which current AI does not have.
And that's fascinating. So maybe it's about, having AI systems that are able to process sensory inputs like we do, as a series of transformations between different frames of reference that can dynamically change their coordinate systems, building a sort of, internal representation of the environment in a truly spatiotemporal way. This might explain how we can easily do transformations in our mind, like imagining an object from different angles or predicting its trajectory. It's all based on some core transformation algorithm. It just doesn't seem plausible that you could do that with deep neural networks alone. We need a completely different type of algorithm. And if it's based on how biological systems do it, even better, then we have a grounding in something we know works.
But you can't just dismiss deep learning so easily. I mean, consider the achievements in image segmentation. We can feed a neural network an image, and it can perfectly separate different objects within it. That is incredibly complicated from a mathematical perspective. And that is kind of understanding the space. It's understanding the boundaries. It's understanding different objects within that 3D space. Or look at the current text to 3D algorithms. They are using diffusion models that were built on the same principles as deep learning. Now they are able to create 3D images from a single line of text. If you think about it, that is a massive leap in spatiotemporal understanding. And these models are continuously evolving. The research into making them better is happening now. We don't need to create a whole new algorithm. We are improving the existing models. We are really close. If we keep this trajectory, we will achieve AGI.
But that understanding is still superficial, right? It's a learned association between, text and shapes. It's not like the model has built an internal model of 3D space. And I still feel that the symbolic representation is critical. Think about the way we use language. We are not just associating words. We are using them to build logical arguments. We are using them to express abstract concepts that exist beyond pure sensory data. We are using logic to create hypotheses, perform deductions, and reason about cause and effect. Deep learning models just don't do this. I think we are missing a crucial piece in the puzzle, a way to combine neural network-based perception with more symbolic-based logic.
And I would add to that the importance of an understanding of time, not just space. Think about playing a musical instrument. You're coordinating your movements with the rhythm. You're anticipating what's coming next. You're constantly adjusting to very rapid changes in timing. Or think about the way we learn to drive a car. We're constantly making predictions about the trajectory of other cars around us. Deep learning, as it exists now, doesn't seem to have this concept of time as a fundamental. It handles time in very specific ways using sequence models. I think that's one of the reasons why it has trouble with common sense reasoning, because it's not really capturing the way, real-world events unfold.
And yeah, so it's about the dynamics as well. Like, what about reinforcement learning? This is an approach inspired by the brain, how we learn through trial and error. Maybe we could be combining this with these spatiotemporal transformation models that I was talking about, that are more based on the underlying neuroscience. Because it seems that this kind of approach is able to deal with complex environments. And, we are still in the early stages of this kind of research, so it's an open field. Maybe we'll discover better architectures inspired by neurosciences that can deal with complex transformations and that can learn from reinforcement in a similar way a brain does. We need to combine the best parts of all these ideas.
But I still think we need to, push the boundaries of what's possible with current deep learning before we completely throw it out. We are constantly innovating. We have new architectures coming out every single day. And like I said before, if you look at recent studies of how simply scaling up deep learning models results in a new range of skills, new levels of abstraction, and better generalization. I think we are seeing that AGI is achievable with this approach. So we should be focusing on scaling our models, not completely reinventing the algorithms. And also, we are understanding these models much better. The interpretability research is exploding. We're starting to understand exactly what these models are learning. So I think we are going in the right direction. We just need to push harder.
I'm still a bit skeptical. It's not only about scaling, it's about the underlying architecture. It's like you can build a bigger and bigger tower of blocks, but it's still going to be a tower of blocks. You are still lacking the overall structure and the framework. We need a system that can really reason about the world, that can understand cause and effect, that can plan sense, that can have common sense, that can build mental models of the world, not just associate patterns. And I don't think we'll get that by just scaling up neural networks. I think we really need to focus more on the neuro-symbolic approaches. We need to find a way to bridge the gap between pattern recognition and logical reasoning.
Yeah, and for me, it's about going deeper than just raw data. It's about understanding the fundamental structure of intelligence. We need an algorithm that's more like an operating system that can deal with different levels of representations, from sensor data to abstract concepts and symbolic representations, and that can seamlessly transform between them. A crucial part of that is how we encode space and time. That's critical. It's also crucial to understand the structure of the real world. We've evolved in this physical space. That's why our minds are so deeply embedded in space and time. We need to look closer into what is the minimal set of algorithms that can perform complex tasks when the agent is embedded in such a complex environment. Current AI doesn't have that. It's mostly operating in a virtual environment where the rules are very different than in the real world. I mean, even just walking is an incredibly complicated problem to solve with different terrains, surfaces, friction, gravity. We do it so effortlessly because our brain is built around the spatiotemporal dynamics of this world. And we are missing that completely with deep learning.
So, when we think about future research, I'm really excited about exploring these more biologically inspired models, right? Like looking at models that are based on actual neural circuits and not just on, abstract mathematical functions. It's not just about copying the brain, it's about understanding the underlying principles of how intelligence arises, and then maybe translating that into something we can implement in silicon. So, for me, the future is in more neuromorphic approaches and in more neuroscience-based AI. It's not about brute force data processing. We should look for more bioplausible algorithms that can learn from data efficiently. And I think combining that with reinforcement learning and that concept of spatiotemporal transformations is something really promising.
Yeah, and I agree that we shouldn't ignore neuroscience. I think it's a great inspiration, but I still believe that the current trajectory with deep learning is the most promising. So, for me, future research should focus on scaling up current models, training them on more data, and continuing to research ways to improve the algorithms. Also, the research on model interpretability is crucial. The better we understand how these models work, the better we'll be able to improve them. I don't think we need to completely reinvent the wheel. We just need to keep pushing the boundaries of deep learning. And also, we need to improve our hardware. If we can create more efficient hardware to run these models, we can scale even faster.
I'm definitely more on the side of exploring neuro-symbolic approaches. I think that combining the ability of neural networks to learn from data with the ability of symbolic systems to reason logically is the key to achieving AGI. So, for me, future research should focus on ways to integrate these two approaches, creating systems that can do both perception and reasoning. And also, we need to look at how we represent knowledge, how we can build mental models that go beyond just pattern matching. So, we should be exploring these symbolic reasoning architectures and the algorithms behind them. I think that is the missing key for AGI.
And for me, future research needs to focus on this underlying spatiotemporal representation framework. We need to understand how intelligent systems encode and manipulate space and time. What are the core transformations that make it possible? I also think that, as I mentioned before, the environment plays a massive role. We should be building AI agents in complex dynamic environments to understand how the environment shapes intelligence. So, a big part of my future research would be looking into the mathematical structures that can perform these sorts of complex transformations, and looking at the biological systems for inspiration, trying to discover the minimal set of algorithms that can produce an intelligent agent in the real world. I think we are looking at it from too much of an abstract point of view. We should bring it down to earth and ground the AI in the real world.
That's fantastic. And it's clear we all have slightly different but complementary perspectives on what the future of AGI research holds. It's so important to explore all the possible avenues. This was a really insightful discussion. Thank you all for diving so deep into this with me.
Yeah, absolutely. It's always great to explore this topic with all of you. It gives a lot to think about. Even if we have different opinions, it's very valuable to understand them.
Yeah, definitely. I agree. It's very helpful to see all the points of view and consider other options that we might have not thought of before. It's a very complex topic, and there are no easy answers.
Indeed, it was great to have this conversation. I always learn a lot when we explore these topics together. It's very valuable for my research. Thank you all.